Good afternoon, well, good evening. Welcome again to this new lecture. Today we'll talk about embedded software design. But first, I want to acknowledge your colleague, Mohammed Qasim. Remember when I pointed to the discussion board last time, and there is a discussion thread about you guys sharing your experience, asking for help, whatever. So this one, the second one. And I was skimming around looking at what people are doing. More Money shared how to configure your USB port, a problem by Yazid, and suggestions how to solve it. Then I found this video yesterday, and you see my screen, right? With code. So Muhammad wrote some code to do a traffic light. Let me run you the video. See, he has a counter here on the 7 segment display, red, green, and orange or yellow sign, like a traffic, emulating a traffic sign with timers blinking and doing some work, which is great at this level. He's using delay loops, he's using parallel ports, he's using the 7 segment display, map, and here's the code. You can download it, look at it, run it even on your computer. And I honestly, I thank you, Muhammad, for doing this. And you're saving me time. I'm writing some simple class demos for you guys to practice. And I see now this is an opportunity for you guys to, whoever does something good and would like to share it with his colleagues, that would be great. Thank you again. Today, I'm going to talk about embedded software design. And I'll cover this topic from my perspective and experience in the industry and reading around. But to give you a brief background about this course, when this course was initially, the very first course description that was written for this course was based on a textbook. That is this one, the second one. I didn't remove it. The department didn't remove it. We kept it as a reference, additional reference. The book, if you get access to it, it's an introduction. In its introduction, and it says who's the targeted audience, and the target audience by the book authors are those practitioners, experienced embedded software design, engineers working in the industry. They're talking about some basic, some advanced things that really we as academicians at this level did not go that deep, like those who are working with embedded software design in the industry. So I thought to present this concept in addition to what our book has, what most of authors in undergrad and grad level courses try to talk about how to design software from requirements to flowcharts, etc., and try to embed my industrial experience here. So I developed some new material. And it will be a good basis for us to build on the model-based embedded software design approach that we're gonna cover in this course, okay? Meanwhile, before I forget, Engineer Raghat told me that she finished grading homework 1. She has, in the feedback, details about how each of the questions was graded or how much you got on that, so you can know where you lost grades or not. She corrected it out of 100 based on a key solution I gave her, but we're all humans. If you see that anything is wrong, you just email her, okay? And everything is fixable. Everything else, keep track of due dates. I was gonna decide. I was gonna record some flipped classroom lectures, but I said, you know, let's push it a couple of weeks. Yeah, I think you're busy enough, right? If you're not, I can always give you more work. You're not?
Busy.
You're busy?
Yes.
Yes. So you have a due date for a lab exercise next week or this week? April 8th. April 8th, right? And okay, no problem. So last time we were here in chapter 2. Let me, all right, this keeps happening, I don't know. Swap. Last time we were in chapter 2. Now I was skimming through the material this morning. You know, chapter 2, chapter 3, I'm gonna skip it. It's about, what was chapter 3 about? It was about a revision, some basic stuff. Chapter 3 was about, I think, yeah, using the board. So we're using the board already. So no problem. So chapter 2, we're gonna finish it really soon. If not today, we already covered most of the topics in it. Chapter 4 is also advanced assembly, and we're already there. We already did loops. We already did a lot of things. So we're gonna finish these few chapters, 2, 3, 4, real quick, and then start in chapter. Even chapter 5 is about, I think, revision. I'm gonna skip 5 as well. Chapter 5 is about reviewing C language and using Code Warrior. Yeah, it's about C. So I'm not gonna. You already know programming. Okay, so then we jump to chapter 6, where we start with interrupts, resets, clocks, all these things. Okay, so we're going to move over there to writing C code. So last time we talked about assembly directives. We already used them in our programs. By the way, did you watch my recordings, the flipped class recordings? With the whole thing is around a few demos, and I write code there and explain some things that we didn't cover at the time of recording the video. Anybody did not watch them?
والله دكتور أنا لسه.
Mustafa, please, before next
لا
lecture.
هاليومين
أنا دكتور واحدة واحدة لا.
Are they boring? مين حضرهم يحكي لي? Anybody watch them?
Yeah, I watched both.
I did.
They're more into hands-on, right? And practice.
Yes, correct. Yeah.
So they're not boring. You can just watch them. You get the experience,
and you get hands-on with the board. So
yes,
yeah,
exactly. So please watch them, guys. If this model doesn't work, we're all gonna lose. Okay, so please watch.
But doctor, if you can put one in a week, better than two. Two is
I understand. I'm slowing down this week, maybe not. Okay, I'll do something maybe next week or something.
Yeah.
Okay, sure. I'll slow down a little. But in case you find something difficult to understand, I didn't cover it very well, you can ask about it when we meet in the class meeting. or ask for an office hour, or use a discussion board, whatever. I can try to clarify things more. Okay, so we covered the directives, macros, and we stopped here, software development process. So in the recordings, that's why I asked about the recordings, in the flipped class recordings, and when we wrote some simple programs together, we said we need to plan for our program. We need to, you want to add 4 numbers together and store the result in a 5th memory location. You need to plan. You cannot add memory locations while they're in memory. You need to bring some of the operands to registers, add, store back, and worry about carry, all these things. And I covered this in my recordings. And so you need to plan. Now planning how to develop software is designing software in a way. So how do we design software? This is the topic of today's class, okay? What our book talks about regarding software development processes, and I'm pretty sure that in your undergrad as well, you went through some of these very basic concepts. Today, we're gonna go a little more advanced. We're gonna talk about, you're gonna hear about some more industry level terms and see something that people actually use in designing embedded software. But what we see on the screen right now, the basics is, first you need to know when you want to develop a software, you develop a software to solve a problem or do something, right? First, you need to know what to do. You need to identify or define your problem that you want to solve, that your software wants to solve, right? So this is step 1. First, you need to know what you want to do. Then, so you need to know what you want to do. Let's say that this is the high level requirement. Okay. Then you develop your algorithm. You develop your algorithm. If you want to call it design your software. Okay. That will solve the problem. That will cover and meet the requirements. And you do this by steps. Step 1, okay, I load, I bring the first operand from memory, then I do add it with the operand I don't know where, then step 3, step 4, and that's it. So you define the steps, how you're gonna approach, what is your software gonna do. And we used it last time, right? In the few last lectures, we wrote steps. Step 1, I'm going to do this. Step 2, I'm going to do this, and so on. These text steps, you can represent them in a graphical format like a flowchart, and all of you know what a flowchart is. But we'll look at it again quickly. After having a flowchart, you design, you write the code. You do the programming. You write code here, right? C code, Python, assembly, whatever. When your code, after your code is running, you test it if it's doing what it was intended for. If not, you go revise your algorithm, you revise your code depending on your requirements. And then you just keep, make sure that your software is updated, looked after to make sure it will consider any changes that may happen. So this is a very high level. I'm going to move to another presentation that I prepared for this purpose. But when we talk about flowcharts, this is what we mean. These are the symbols of a flowchart, you know. A terminal, when you start, say, so, right? You start your algorithm, then you do a process, you add, right? Then you check if A is greater than B, if it's true, right? You do something, if false, If false, you do something else, right? Or you can loop back to somewhere at the beginning, then you do something else, right? At the end, you end. Oops. Then, oops, I'm sorry. What's going on here? Then you can terminate, right? A terminal, you end. The difference between software design in embedded systems and non-embedded systems is that the software doesn't ever end. There has to be an infinite loop, and we saw this in our examples, right? So if any of you draws a flow chart for a design when designing a software in this course, you will have all these steps, and at any point of time, there will be an infinite loop, right? Regardless how the details, after checking a condition, whatever, doing something over and over again, and there is no end. The software, the embedded software does not end. Okay, this is about the symbols of flowchart. So, and he's given you some few examples here. I'm not going to write any assembly code from now on. We're almost done. In the class demos we did, we wrote, and we addressed most of the problems he's talking, adding 3 memory locations together. So first, he wrote the steps down, then converted it into code, or draw a flow chart of what he's doing, the steps in graphical display, then convert to code. Okay, I'll come back to here. I'll come back here to talk about more technical stuff after we finish, or I cover the embedded software design. So I'll upload this to e-learning. So we're gonna talk about the following main points when we talk about embedded software design. We're gonna talk about the process of designing software, or embedded software, embedded to be more precise, because I'm not really experienced or that expert in other software processes, but I'm talking about embedded software, starting from putting the requirements till you get production executable code. I'm going to talk about what is requirements engineering. I'm going to show you some requirements tools. I'm going to talk about software requirements methods and tools used to by requirements engineers. Then I'm going to talk about verification and validation of embedded software code. I'm going to try to make it a little fun, or not fun, but not, at least not boring, by showing real industry examples here and talking about what people do. Some of the stuff I'm going to keep it until after the recording, okay, for IP purposes. Okay, I don't want to put some of the stuff public, but at least I'll point to the methods, to the software, to how to do things. When showing examples, in some cases, I'll keep it until I end recording. When I first started covering this topic in the classroom, I really didn't have enough notes, and you can rarely find something really practical that you do cover in such a class. So I used to use my experience, my memory, some documents I have from previous work, and I use the board. So I thought to put this picture here, but since we switched to online, and this was a driver to develop better presentations. Okay. So when you want to design a product, the thing starts with the product owner, right? Or the customer, or the top management, or the person who's going to pay for the product, right? The only exception where the customer did not know their requirements or did not define their requirements was, I like the story when Steve Jobs was introduced the iPhone for the first time, and people were saying, "You're crazy. Why do people want to use a touch screen? And a phone is you use it to talk and buttons to dial numbers." And his argument was that many of the people don't know what they want. I'm going to tell them what they're going to like, and they will start liking it, and they would ask for it later. But in many cases, when you design a product, the head, the board, the CEO, defines the product requirements. And at this level, when we talk about embedded software design, I'm not talking about product requirements. I'm going to talk about embedded software requirements. So we're going to go one step lower to functional requirements. Okay, but to cover the whole, to cover the big picture, I'll come back to these texts. I don't want to show you texts, بصراحة. I'll come back to this text in a second and try to use the board, and but you can keep this for okay. What is this? Hide. I'll come back to these slides in a second. Let me try to. So I'm going to talk about high level, or not high level, lower level, lower than the product specs or needs. I'm going to talk about software requirements, functional requirements. So when you have a product, right? High level requirements are defined by senior management, by customers, right, etc. Then the product could be, if it's a complex system, could be divided into subsystems, right? Subsystems. And here starts the project management process, from managing the subsystems, putting them all together, and even project management at the level of a single subsystem, right? Now, a subsystem could be the software, the embedded software that will solve, for example, that will control I don't know, will control the turbo charger in the vehicle, for example. Another embedded software model could be the software model that will be controlling the injection of gas and looking after the closed loop, the fuel injection and exhaust, and controlling the amount of fuel in the combustion engine, etc. Okay, so you get that component. After what you know what component or what subsystem you're going to deal with, you start, okay, doing, if needed, some advanced research, before starting the work, right? Advanced research, if you want to call it, some R&D, to know what you're going to do before going to production. Afterwards, when you well understand what you're going to do, the process of developing the functional requirements. Should start. And here, the role of requirements engineers start. I know some of you non-industry people are saying, why is this important and trivial? But I personally, I did not appreciate it before going to industry, and figured out all these kind of work, planning for things, documentation, and all the details I'm going to talk about. Take the maybe 90% of the effort, time, labor, brain power, and the writing the actual code is probably the easiest thing to do. Okay. And we're talking about functional requirements. We're talking about engineers here who understand and know what they're doing. And I'm talking at a level, let's say a controls engineer who wants to control the turbocharger in your car, a turbocharger. This person should know what a turbocharger is. How does it work? What the exhaust comes from the, when the exhaust comes out from the cylinders from the engine, and goes and moves the turbine or the turbocharger, and how to control all the components of that charger, the wastegate, the surge valve, the blah, blah, blah. He needs to understand the hardware. He has to be an engineer. Then he needs to do control. Okay, how do I control the position of a gate or a valve or something when I want to open it? Do I need to use a PID controller? Do I need to use a different kind of controller? A PI, maybe you don't need a D, whatever. He needs to be a well-experienced engineer. What is my feedback loop going to be? What's the source of the feedback? What is the variable I'm going to control? How I'm going to tune? Okay, so we're talking about functional requirements, not somebody not knowing what they're doing. We're talking about engineers, experienced engineers. And this is probably the most senior engineering job in this whole process. Okay. Now we're talking about generic terms, requirements engineering, but if the kind of embedded software you're developing is to control stuff, this guy could be called a controls engineer, right? If this software is to do onboard diagnostics, for example, in a car, this person could be called an onboard diagnostics engineer, requirements engineer, whatever, production engineer. Now the output of this process is functional requirements. functional. I'm going to spend a little time here. Requirements and how requirements and how to define these functional requirements. So functional requirements document. And since we're talking about software, some people call it software requirements document. In industry, we used to call it SRD. SRD, software requirements document. This document, I'm going to spend more time. This document can range from a text file, flowchart, MATLAB file, and I'll show more details about this. طبعا, of course, if the software exists and you're to use it or modify it to solve other problems, maybe you need to get managerial approvals before producing the software document. Maybe here at this level or even the level before, maybe you will need to do a requirements change notice. Don't worry about, just listen to me and don't worry about if my handwriting is not clear. I have the slides, I'll show it. Requirements notice change, they call it, we used to call it in industry RCN. So you submit an RCN, you ask to modify the requirements of a certain software, or even to create a requirements for software. Because when you want to solve a problem to control the whole engine thing in the car, how many software models do you want? Do you want one model for controlling the gas injection, one model to control the turbocharger, one model to control the onboard diagnostics, or do you want a few together? So management here, technical management, need to meet and understand what are you trying to do and get the approvals on this software product you're gonna produce, okay? So a managerial thing, but important, technical managerial. Then you produce the SRD, and this is the most important thing right now, software requirements document. The software requirements document, the SRD, when it is produced in industry, I'm talking about industry, it goes to somebody. So here we talked about who produced this, a requirements engineer. And this could, engineer, this could be a PhD holder, or could be a graduate level, or somebody with a very high, long experience. Could be a controls engineer. Okay, whatever. So we have first level engineer here that produces a software requirements document, functional, and I'll show samples of these. This shall go afterwards to a documentation engineer. And you don't believe how important are documentation engineers in this process. They're responsible of making the software requirements document, include anything that can make it sustainable. You may write software that would be still used by generations of engineers after you for tens of years. So anybody that comes after you shouldn't reinvent the wheel, should be able to build and understand what your software does and be able to modify it accordingly. So the documentation engineer will make sure that the revision history is there, even the color code of writing. I also show examples, but when you write your requirements, what you write in red is different than what you write in blue, what you write in green, okay? So there is a documentation engineer that comes right after the functional engineer to make sure that the SRD, the software requirements document produced by the controls engineer, for example, is usable and meets the requirements. And guess what? There are standards in the automotive industry. There is an association called SAE, Society of Automotive Engineers. This is like IEEE, but for automotive engineers. They have requirements on how a software requirement document in MATLAB should look like. What is the color of the line connecting two blocks? What the block color should be if this is a RAM variable, or if it is a RAM variable, or if it is a constant, or if it's should be in E square prom, okay, a calibratable. They go to that level. So after documentation, engineers, you guys with me, right? Didn't fall asleep yet?
Yes, with you.
Okay. Any of you guys in this field from the industry? Talal, Ahmed?
I am from the IT broadcast section. I'm working for a manufacturer. We have such a model, but in different names, different, for example, we have a product manager. We write a document called the statement of work. Something similar to what you said now.
So the big picture is almost the same. Or close. Okay.
نفس الشيء، بس احنا عندنا واحد ممكن يعمل الاشياء هاي كلها في شركات الاردن اغلبها. ماشي مقسمين بين الانجينيرز انه ديزاين لحال، البروجرامر لحال كذا. لا قبل فتره فهمت علي كيف؟
Yeah, it could depend on the size of the work, what you're doing, what you're producing. I'm talking here about my experience in the automotive industry, where, at the end of the day, in your car, you have one engine controller, right? This engine controller, the computer, the engine computer. This engine controller, hundreds and maybe in some cases 1,000 of engineers could be working on designing that software running on this piece of hardware. Okay, different kind of software modules, doing different things. Software engineers converting these requirements into code, making all the code meet the requirements, run on a single hardware, documentation, calibration, depending on the size. But let's try to understand the big picture. So after documentation engineer, and this is an engineer who knows what is a RAM, and what is a read-only memory, what is a E square prom, and what is a calibratable, where should it be put? An engineer, okay? Then could be, so the SRD comes out of here after being revised, then could be the calibration engineer. In your code, for example, controlling the position of the position of the throttle body, for example. Of a throttle body. You have a required position. You get feedback from sensors, right? You take it to a PID controller, the error. Okay, you produce the required, for example, PWM for the throttle body, reflect on the throttle body, for example, position, right? And you get the feedback through a sensor that measures the angle, and so on, to control the position of the throttle body. So the calibration engineer, the requirements engineer says, I will need a PID controller here, a PID controller. But, you know, a PID controller, there are gains like KP, KI, and KD. And these values depend on the throttle body size, on the signal coming, on the type of sensor, and how fast you want the response versus what is acceptable error to be there, etc. So a calibration engineer comes and calibrates all these variables to meet best performance needs. Okay, so this guy is an engineer. He sets the values of these gains, for example, for a PID controller, but to be able to do that, he would need to understand what is a PID controller. Okay, you say if the temperature, the ambient temperature in the vehicle is greater than or equal a calibratable value, for example, a constant, okay, calibratable, do this, right? Do something. Else, you can do an else. The calibration engineer would figure out what is this. You as a functional engineer, a controls engineer, you say, I need to compare the temperature with a constant. What is that constant value depends on what you want to achieve. So the calibration engineer should understand the software, what it is supposed to do, and go calibrate all these variables, constants, and of controllers or anything else. Okay, so again, we're talking about an engineer who knows what he's talking about. And by the way, since we're talking about throttle body, you know what a throttle body is? Throttle body. No? A PID controller? No?
PID controller دكتور.
Tell us, Mariana, what is a PID controller?
يعني هلا بكون عندنا انه انبوت بنحطه على PID controller عشان يصحح لنا انه الايرور لحتى انه نوصل انه للاوتبوت. بنحط انه بين الانبوت والاوتبوت بنكون في عندنا زي فيدباك لوب زي نحط سنسور او شيء زي هيك.
اوكي يا
يعني ها تقريبا PID controller. اما الاولى لا ما بعرفها.
Did anybody ever write a PID controller by software?
دكتور انا PLC بس مش كودينج.
Using PLC. Okay. 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 طيب, let me try to a throttle body. You know, when you hit the gas pedal in your car, دعسة البنزين.
Yes.
كل ما تدعس بنزين, when you put when you push the gas pedal more, the car starts moving faster, right?
صح.
Yes.
انت بتدعس بنزين صح؟
صحيح.
you're injecting more gas into the engine. That was true in the past. In today's modern cars, it's not a throttle body. You can call it if you want بدل دعسة بنزين دعسة هواء. What actually happens in the gas engine, if this is a cylinder, a 4-cylinder car, there are inlets that allow from one direction or through a valve gas to come in through the injectors. So if you have an injector, if you run, you inject gas in the cylinder, right? And here's the piston. And oxygen should come in as well, right? In the past, we used to inject gas. The gas paddle and used to directly affect how much you're gonna have gas come in. In modern cars, no. When you push the paddle, the computer reads the angle, how much speed you're asking for, how far you're pushing your paddle, and then injects or allows oxygen or air to come in. If it is naturally natural aspiration or natural air comes in due to vacuum, that's natural. If you're using a turbocharger or compressor to push in more air to get more power, that's also possible for turbo cars with a turbo. So a throttle body is something like this. Okay, a body from a metal type of thing, and you control through a servo motor, for example, here, something to make this body. Imagine you have a circle. If you see my hand, and this is something that can turn around its center. So if this circle is here like this, if the air is to come this way, it is closed. You don't have air. If you push your throttle paddle more, this will open more, a little more. So you have some space for air to come in. If you push more, it will open more. More air will come in. Okay. So you control the amount of air that comes in here, and based on this air and the exhaust, okay, the exhaust coming from all the cylinders, okay, being collected in the exhaust. There is a catalyzer usually. صندوق البيئة بتعرفوه صح؟ Usually you have an upstream O2 sensor and a downstream O2 sensor that measure the amount of oxygen. ميكانيكية here they call it زطمة الأكسجين. The O2 sensor measures the amount of oxygen in the exhaust, and this will go to a computer, the computer, to adjust how if you need to increase or decrease the amount of gas that should be injected based on the oxygen you allowed to get in. So you allow more oxygen, there should be a controller, for example, in the computer. You allow more oxygen to come in, then you should inject more gas to burn it, right? If your exhaust has more oxygen than that is acceptable, the ratio of O2 to fuel, they call it lambda. If O2 is more than the amount of fuel, then you did not burn very well, right? You need then more gas to burn the oxygen. So you inject more gas and so on. That's why when your O2 sensor is not working properly, your car will start consuming more gas, right? Anyways, that's the throttle body. A PID controller, on the side, I wanted to talk about this. I know all of you here in Jordan, everybody studies control systems in their undergrad. And they usually do the analog control and concentrate on controlling models with a transfer function and at that point of time, they never knew before about Laplace and S transforms. So they spend a lot of time learning those before they come to the actual control. And before they end the class, there is not much practical side of it. And they don't cover the digital control part, where you don't need, instead of using analog devices, how to write code to do this digitally on a controller. Speaking about this, I want to share with you, are you interested to hear more, or should I go back to the software design? The problem is I don't see your faces, so I don't know.
Let's go back, Doctor.
Let's go back? Okay, sure.
Let's go back.
Right. So the calibration engineer should be able to calibrate controllers, calibrate thresholds, whatever. So he's an engineer. Afterwards, after the calibration is done, understanding that the calibration engineer uses tools to calibrate. So he starts running, for example, looking at his controller. Oh, the amount of exhaust, the NOx, for example, the NO or the CO2 or whatever in the exhaust is beyond what the regulations allow. So you need to go work on tuning some parameters in the controllers to reduce or decrease these gases in the exhaust. So some testing has to happen while calibration. So while calibration, you calibrate and test to calibrate. Some in some industries, we used to do this on Hill. Hill is for hardware in the loop. Hardware in the loop. Hardware in the loop, software in the loop, where if you cannot, or if it's difficult to simulate a piece of hardware, you can use it in a simulation environment, still using hardware and testing. So in the health, in automotive, for example, we used to have something simulating a car. So you sit in front of a computer and you start driving and monitoring everything. So there are Hill engineers who design your simulators. But afterwards, something to bring you to reality, afterwards you can do it on the actual hardware. You put it on the controller of a car, okay, and go drive and test and calibrate a continuous process, okay, until you get the results, okay. Well, the SRD for the calibration engineer to run it, to be able to run it on a car, it needs to be part of an executable code. So who makes the executable code? I'm sorry, I forgot this part. There is here, I told you, it's the software engineer. So the software engineer. The software engineer receives an SRD from this requirement engineer, another SRD from another requirements engineer, another SRD 3 from another requirements engineer, puts them all together to produce one executable code that will run on one single computer. Then the calibration engineer, you will have a calibration engineer for this control loop, another calibration engineer for another, and so on. You test it. You have this control loop. You can go back to calibration. You can go back to the software. If you find software bugs, you can go back to the requirements, even if you found out that some requirements were not correct, until you get to the test engineers. Okay, any feedback can come after after calibration or testing, to test for all possible scenarios. So here we're at the verification and validation process. I'll talk about it more. You can go send feedback, and if everything is okay, you have your production software, embedded software. Okay. I'll go back to the slides. I'll go back to slides. For those who are interested, because طيب خلاص, okay. So this is roughly the process. I'll go back to what I tried to summarize here. Okay, this is what I summarized. Okay, and when it gets to the embedded software design, we start with a request to modify or create a new software requirements document. A requirements engineer or a product engineer, a controls engineer, if you will, would define the functional requirements, produce a software requirements document. And this document, again, it's not a document. It could be a Word document, a text document. It could be a MATLAB executable code. I'll come to this, okay? You get us an SRD. I'm going to talk about these types of SRDs or software documents in a bit. Then this SRD, along with the design, verification, procedure, and report. Who knows how to test the software? The people who wrote the requirements for that software. So you produce a software requirements document and the design verification and process and report document that would tell the test engineers afterwards how to test this software and make sure it met the requirements. Goes to a documentation engineer, then to a software engineer, produce the version 1 of the code, phase 1, phase 2, whatever, test engineer that tests the software against the requirements, the verification process on a hardware in the loop or emulation environment. A calibration engineer will calibrate all the variables and gains, send feedback to any previous stage, okay, then produce the software. And this summarizes what I was explaining on the board. Why requirements engineering is important? A study, here are the references here in the bottom. A study by the US Air Force showed that 41% of all project errors they did happened in the requirements phase. Because you had wrong or inaccurate requirements, you get errors in your product afterwards. And the percentage is 41. And it is the largest. So if you don't write your requirements correctly, you'll get more problems. Another study showed that 80% of time spent on rework, and you produce something, you go fix a problem, okay? 80% of the time spent on fixing problems was due requirement errors. So take your time, spend a lot of time on the requirements so you can reduce the time and problems you get afterwards. And this is the relation, roughly, that describes the cost of defects at every stage in the cost of fixing a problem at the requirement stage is low. In the design stage, it's more, but still not comparable with something that is operational. For example, a callback for a car that is already in the market, okay? or in the testing, it is less than something operational, but it is much more the cost here than if the error happened when the, or any, to fix a requirement error at this stage of time is much less cost than fixing it after you get to the testing stage or the operation stage. Okay, so why is requirements engineering important? To save time, money, get closer to what you want to produce. And this is very important, eliminate or reduce mind reading. So what does the, a software engineer, when he writes a code, he shouldn't just start writing code and then somebody asking him, why did you do this? Why didn't you do this? Well, he doesn't know, you didn't tell him. You need to document everything. Speaking is not enough. A document has to exist. And by the way, this reminded me of software engineers. You know, there is a major in universities today called software engineers. Do you know what is the origin of this name? Where did it come from? It came from the automotive industry. They needed engineers who write code, who also are engineers, electrical and electronics engineers, who understand control, who understand engineering to be able to write software. So they call them software engineers. Then the thing flipped. The major taught in universities today is about engineering software, how to engineer software, how to manage requirements, move it on, test it, etc. Anyways, okay, when you want to define your requirements, there are some known best practices and things you should do. Some of the recommendations, you should use short and simple sentences. Any requirement shall start with the word shall. You don't say, so you say, the system shall be able to operate in a temperature between minus 20 Celsius and 100 Celsius. Shall. You don't say should. Okay. You don't say must have. Shall. Should be clearly written. Not contradictory. A requirement should not contradict with another requirement. You shouldn't be redundant by putting two statements that cover really one requirement, and should be testable or measurable. So you need to have a criteria or a way to measure it afterwards and make sure that the requirement was met or not. Okay, traceable to parent requirements. So sometimes you have sub requirements of a parent one, more detailed. When you write your requirements, you try to avoid some escape clauses like as appropriate or as necessary. So you don't say the software shall be able to control the RPM of the motor to run in appropriate speed or an acceptable. These words you should be precise. Your requirements should be measurable. You say from 30 RPM to 50 RPM, for example, you get quantifiable, okay? But at this stage, if you don't really know how to write something or you're not sure about it, just write it down and do the loop and keep revising until you get to something perfect. At any case, you find if somebody wrote a requirement and there was an and, you need to double check if the two sides of the and could they be broken into two requirements, for example? then if so, yes, you should split them. Don't forget to include derived requirements. An example how to write a requirement, for example, then you name the system shall be able to do something, function, object within time unit from, this is an example. So PowerCal to some kind of software shall be able to generate and something EFT file within 2 minutes. You don't say quickly, within 2 minutes exactly from the time the calibrator passes the run button, for example. So shall, measurable things, defined types, okay, references, and so on. An example, the wastegate should be closed at the low engine speeds to minimize fuel consumption without a back pressure penalty. This is a bad statement for a requirement. This is a suggested better statement. For example, a wastegate is a gate in the turbo of a vehicle turbocharger. Wastegate position shall be calibratable by the calibration engineer. So can be closed at engine speeds lower than X and back pressures not greater than Y. So you gave measurable, quantifiable requirements. Sample requirements. Okay, I think I need to hurry a little. There is a software by IBM, okay, IBM called Doors. Well, this is something I used. There may be much more, but this is a very famous one, expensive one. Doors is stands for Dynamic Object-Oriented Requirements System. It's a software where you define your requirements. Okay, I'm not going to spend a lot of time. You can read it. The good thing about Doors, this is a screenshot of it. I don't want to show more details, but every requirement will get a number. It can be tied with statements in Word, in MATLAB, in multiple SRD formats, where it makes it easier to go check for a requirement, even while writing the software, while testing, while reading feedback, while calibrating everything, to eliminate or reduce the possibility of having requirement errors. Okay, how do we define our software? The software requirements document. First, there is a way by text, writing pseudocode, for example. You say, check, like the thing we saw in the previous. So step 1, do this. Step 2, check this against this. If this is greater, do this, okay? A text document. I'll show you an example. And there is another way, a graphical method. The graphical method, you can use flowcharts that we just saw. We can use model-based tools, and we're going to spend time here, okay? And we're going to actually use these tools to define software and produce code. This is the approach now in many industries, in automotive industry mainly, and other industries. You visually design your software. You don't do flowchart. You use the blocks in MATLAB Simulink, draw your software. That helps you while putting your requirements to simulate, or even in cases, do rapid prototyping, generate executable code, test it, and go fix your requirements before going through the long chain that we just explained. Because if you're at flowcharts or text, before you get a chance to get an executable software to test, you need to wait until all softwares are collected from all teams and go through all the processes and get one production software and go test it. Okay, model-based tools. So in our plan, in the course description at the beginning of the semester, we said we're going to cover model-based embedded software design. Okay. Within MATLAB simulating, there are state flows. I'll show some example and other methods. Of course, LabVIEW has, National Instrument LabVIEW has tools and maybe some other vendors I'm not aware of, but just to show what is model-based and how important it could be. This is a screenshot from a real-life SRD. This is how they write it. Colors, statements, equal, do. When you want to correct something, you cross it over, and in the revision history, it shows who crossed this out and where the highlight where the modifications were done. Text. To get the software, you need to wait the software engineer to give you the software. You test it, then you go back to the requirements and fix it. While in flowcharts, you know flowchart, this is a graphical way of representing a software design, model-based. And this is something we're going to do. And I don't want to waste time flipping cameras, but I have prepared something here on my desk to do some implementation of some using Simulink. But the idea is, this is, you define your software. There are standards where you can look from the colors, from the blocks, how they look, you can understand what this software does. While this software with a button, you can simulate, or then you can generate code to run on actual target hardware. At any point of time after simulating, you can go fix requirements, or even after the embedded software is generated, either through autocode generation, you can go fix software. And even, I didn't draw this here, after a software engineer gets the requirements from all the teams and does the operating system configures the operating system to run all the different pieces of the software or the tasks and create an executable. Okay, you test it, then you can go back fix. This is the case before using model-based. When you did a text, you needed to wait. You were not able to simulate. You were not able to generate autocode. You needed to wait the software engineer to put all pieces of software together and give you an executable that you can test. Imagine how much time model-based saves, and saves time and cost in fixing problems. Some examples I had from my work with an airplane. This is an airplane. In this code, in this airplane, I'm controlling a quadrotor here. I'm showing, this is for visualization only, but what I like to put the slide here to show you that the gains that I used for the 4 PID controllers for this airplane in this stage were the gains, and whoever worked with controllers will understand what I'm talking about. The gains I used here in simulation were the same numbers put on the actual hardware when the drone was flying. I did not have to change a fraction or fine tune anything. This is how much this helps. An avionics system, I don't know, should I move faster or keep it until next time? I want to show you more about PID, state flows, share some experience here. You know what, I'll finish this next time. So we stopped at model-based, okay? And maybe next time when I finish this presentation, we go design some embedded software with MATLAB Simulink and run it on our Arduino. You will need to be able to use this. You will need to have MATLAB and Simulink. This is available on campus in our computers on campus. And because of the pandemic, I think you have 2 options. to have it. If you have MATLAB, that's great. If you don't, you as students can buy a student version that I think is like $55 with all the components. Option 3 is to ask Muad Kundil how to do it. He has a secret way of doing it. Muad is with us in class, right?
نعم موجود.
Muad can help you how to access it. Can't you, Muad?
أكيد.
Okay.
أكيد أي حد بده يبعث لي.
Okay. If you need help with MATLAB, Simulink, autocode generation, setup on your machine, communicate with Muad. I'm going to stop here. I don't want to move faster. Okay. But I think we're going to finish this next time and move to hands-on. Okay. If you don't have any questions, if you have any questions, you can say until after I stop the recording. If you don't, you may leave, and see you Monday, inshallah. Thank you very much.